Hi folks, I've got a video for you here on factoring large polynomials. This is part of our chapter 4 material. Ideally, this worksheet should be done once you've gotten through or at least worked on your sections on rational zeros of polynomials and complex zeros and the fundamental theorem of algebra. So if you've worked on those sections, great. If you haven't yet, you should probably at least look them over and fight with them for a bit before going through this worksheet. The idea of this worksheet is to kind of bring it all together as you get ready to move to your sections on rational functions. This worksheet here that I'm working on, I sent as an attachment to the email that announced this video. It should also be online as a link near where I have this video stored on my website. So look for those things. If you haven't got this printed off yet, it really is nice it's kind of built for us to follow along. Then there's another one that you can do on the back of this that you can do yourself for extra practice. But if you don't have it yet, stop the video, go get it, print it out so we can follow along. It also makes a nice model for when you're working on stuff later. Okay, so we're going to factor this big polynomial. One of the first tools we're going to use is your rational root theorem, sometimes called your irrational zeros test. And our goal is to break this thing down into factors. In this problem, initially, we're going to do this as irreducible factors, but we're also going to, let me fix that. We're also going to look on how to break it down into full complex factors, as we're going to tend to do in once we get the fundamental theorem. So we'll talk about this irreducibility once we get down to the end. So the rational root theorem talks about the fact that when we break this up into pieces, this is a 6th degree, so ideally we'd break this into 6 factors. And each of these AXs out in front, this AX and the other AX, these are not necessarily the same. When we multiply all of these AXs together, they should multiply together to make this 4x to the 6th. And all these constants, the b's, all the b's should multiply together to make this -4. All these others come from the interaction of some b's and some a's and some x's all multiplying together to make the mess that's in the middle. But the 4x to the 6th, the lead term, and the -4 are really isolated because they are built from only the AXs, make the 4x to the 6th, and only the b's make this 4 at the end. So that's actually very handy. A factor like ax minus b, if you set that equal to 0 and solve, that root, that 0 of the polynomial, has to be of the form b over a. Set this equal to 0, solve, add the b, divide the a. So all of your factors, if they are rational, should be of this form. Now there might be some irrational number in here that's making this 4, or even some complex numbers that are making this -4 at the end. But if they're rational numbers, they will be of this form. So if we look at all the possible rational numbers that could have made this -4, it could be a 1, a 2, or a 4, and it could be positive or negative. We have to keep track of those. And this a has to be something that's a factor of the 4. So it could be same plus or minus 1, plus or minus 2, or plus or minus 4. So any rational zeros have to be something from the set of factors of the constant divided by something that's a factor of the lead coefficient, because that's what all our little solutions are going to look like. So if we're asked to make a list of possible rational zeros, we just want to list all the possible things that could be made from this. So we could have 1 over 1, that's 1. We could have 1 over 2, 1/2. We could have 1 over 4, 1/4. 2 over 1 is 2. 2 over 2 is 1, we already have a 1. 4 over 2 is 2, we already have that. I missed one. 4 over 1 is 4. 4 over 2 is 2. 4 over 4 is 1. 2 over 4 is 1/2, we already have that. So all of those combinations make this list, again, positive or negative, of these 10 possible numbers. Now, that does not mean these are all of our zeros, but that means that if this function has a rational zero, it must be on this list. So keep that in mind. If you're asked to find the possible rational zeros, you're not actually asked for the zeros or the solutions. You're being asked for this list. Don't overcomplicate that question. Now, we could continue this problem by just taking all 10 of these. There are 2 for each for the plus or minus, so there are 10 possibilities here. We could take each of those possibilities, do our synthetic division with our big polynomial, and see which ones work and which ones don't. But checking 10 isn't so bad, but sometimes this list of possibles can be 20, 30 numbers long, and we don't want to check them all. So a nice thing to do is combine this list of possible zeros with the graph. Now there are things like Descartes' rule of sign and some other tools that are a little more old-fashioned and very, very handy. But now that we have our calculators around, it's nice to just go and grab and look at, hey, what does this graph look like? Now, depending on the scale of your window, it might look a little different, but you should more or less see this interaction occurring in your graph. Now, the nice thing about having both the graph and this list is, say we look at this graph and decide that, hey, this point looks like it's -3. Well, -3 is not on our list. So it can't be the rational number -3. It could be some weird irrational number that's close to -3, but it won't actually be that -3 if it's not on this list. Also, this +4, for example, if +4 is way out here, the graph doesn't pass through +4 way out here, so don't check it. If something looks like it's a 0 on the graph, if you look at your numbers, that looks like about a 1. This looks like it's somewhere near 1/2. This looks like it's somewhere near -1. If 1/2 occurs on your list, great, try it. If -1 occurs on your list, it will tend to, try it. If 1 occurs on your list, try it. So combining the graph with this list of possible zeros can really quickly break down into good places to look, good values to try. Now I'm going to start with this +1 because positive ones are fun to work with. But before we do that, I want to observe something real quick. Notice we have 1, 2, 3 zeros that we've listed here. Since this 1/2 seems to bounce, it probably has a multiplicity of 2. So that's 1, 2, 3, 4 zeros that we're seeing. As a 6th degree polynomial, this thing should be able to have as many as 6 real zeros. Now it's possible that the graph goes back down and generates another 2, or this way generates another 2. But it's also possible that those missing 2 are complex numbers. So in our section on the fundamental theorem of calculus, we need to be able to find the real and the complex zeros. So we'll have to hunt down those other 2. We'll talk about those later. So we can check to see if this -1 really is, this +1 really is a 0 by, you could have your calculator evaluate it and see, or we could test it really quick with synthetic division. Now I've listed out the coefficients here for the synthetic division, checking to make sure I don't have any zeros. This is a 6th degree polynomial, so it does go 6, 6th degree, 5th, 4th, 3rd, 2nd, 1st constant. I like to do that when I'm setting up synthetic division. It's a 6th degree, so it should go 6, 5, 4, 3, 2, 1 constant. If it doesn't do that, you're missing a 0 placeholder. Be very careful about those. Those get people on tests more than almost anything else. So I'm going to perform the synthetic division with the 1, because it looks like it goes through 1. And let's just do this real quick. Bring down the 4. 4 times 1 is 4. Minus 4 is 0. 0. Bring down the 13. 13. Bring down the 1. 1. Bring down the -12. -12. Bring down the 4. 4, 0. So it does work. So we've proven that the x minus 1, notice that is the 0 for x minus 1, minus 1 is a factor. Now we could have shown that other ways, but the nice thing about doing it with synthetic division is not only have we proven that the x minus 1 is a factor, but we've also broken this 6th degree polynomial up here into this 5th degree polynomial. This is now 4x to the 5th, 0x to the 4th, 3rd, 2nd, x to the 1st, and a constant. So we've made this 6th degree polynomial into a 5th degree polynomial and begun the process of breaking this problem down. So when we go to pick our next thing to check, the 1/2, we're not going to do that 1/2 on our old polynomial. We're going to do it on our new reduced polynomial. Then subsequently, this thing will get smaller and smaller every time we find something that works. Okay, so again, let's just do the synthetic division real quick. I'm going to bring down the 4. Half of 4 is 2. 2, half of 2 is 1. 14, half of 14 is 7. So 8, half of 8 is 6. So, did I do that right? So negative 6, half of negative 6 is 3. That didn't work. Because half of 8 isn't 6. Half of 8 is 4. Sorry. So negative 12 plus 4 is negative 8, making that a negative 4, making it a 0. It had to work in there somewhere. Now it's possible that it didn't work, in which case this would have been an irrational number that looks a lot like 1/2, but I was pretty sure it was 1/2. So do be careful with your mechanics there in your synthetic division. So again, that verifies that x minus 1/2 is a factor and breaks us down from a 5th degree to we're now a 4th degree. Now something dangerous is happening here. You have to be a little careful. This 1/2, I said earlier really fast that we notice it bounces there. Because it bounces, there's a good chance, or looks like it bounces, there's a good chance that this 1/2 has a multiplicity of 2. That 1/2 is occurring as a factor twice. This is actually supposed to be x minus 1/2 squared. If you haven't reviewed your section on multiplicity, be sure to do so. It can be very, very handy. But the big thing is, if we see a bounce like that, or the root kind of slide through, it's often handy to check it more than once. Always keep in mind that a 0 can work more than once in your synthetic divisions. So if we try that 1/2 again, because it looks like it bounces, we're going to, again, get the 4. Half of 4 is 2. 4, half of 4 is 2. 16. Half of 16 is 8. 16. Half of 16 is 8. 0. Hey, I got it right that time. So it does work twice. So this is really x minus 2, sorry, minus 1/2 is happening twice, because that multiplicity is causing that nice little bounce. So be sure to get used to the idea of just because it works once doesn't mean you can't try it again. If you're really stuck and you think, I've tried everything, I can't find something else that works, try the things that already worked. It's quite possible you have a multiplicity. That's one of the big reasons that using both this list of possibles and the graph together can be really helpful. So those two, or in some ways those three, work nicely. Let's try the negative 1. Try the negative 1. Bring down the 4. Negative 4, 0. Was it 0? 16, negative 16, 0. So great, that one worked too. So we verified that x plus 1 is also a factor. And we're left down here, because we did our division subsequently on our results, we're left with this 4x squared plus 16 as that last piece. Now that 4x squared plus 16 has no x-intercepts. If you could factor it a little bit, bring out that 4, x squared plus 4 is nice. We'll talk about what to do with that 4 in a second. But x squared plus 4, that's a parabola. It's lifted up 4. It has no zeros. It can't be factored anymore. If you did your discriminant, you'd get negatives, start getting imaginary numbers. This is what we mean when we talk about irreducible factors. Irreducible factors you can't break down anymore without getting complex answers. Irrational ones are okay, but not complex. So if you were answering this question straight based on being told irreducible factors, you'd have 4 times the x squared plus 4 times all of these. The x plus 1, the x minus 1/2, the x minus 1/2, and the x minus 1. Now, a couple things to clean this up a little bit. Notice the x minus 1/2 are kind of ugly. And often you'll be able to fix that. Notice if we multiplied this x minus 1/2 by 2, you'd have a 2x minus 1. That would be prettier. Multiply this x minus 1/2 by a 2, and you'd have, again, 2x minus 1. So if we had a couple of 2's, we could clean those up nicely. Well, look, they're over here. This 4 is 2 times 2. Put one of the 2's in there. Put the other 2 in there. And you will get a much more attractive x squared plus 4, x plus 1, 2x minus 1, 2x minus 1, and x minus 1. And frankly, I'd even be inclined to write this as 2x minus 1 squared to give a nice, pretty final answer. Now, that breaks us down to irreducible factors. So if your question says irreducible factors, then you're done. But we can break down this x squared plus 4 more. We can find its solution set equal to 0 if we are okay with dealing with complex numbers. It does have solutions. Plus or minus the square root of negative 4. We can take the square root of negative 4. Square root of negative 4 is just, so we got plus or minus 2i. Oops, sorry. So those are a couple more zeros of this, or roots, of this big polynomial. So we now have, from this start up here, I'm going to start with the x plus 1 for no particular reason. So x plus 1 times 2x minus 1, I'm going to write that as squared, times this x minus 1, times these two x plus 2i and x minus 2i. And that forms your fully factored and factored into complex solutions. Now, if you were asked what are the, let's say instead somebody said, instead of factor this, somebody said set this equal to 0 and solve, you'd have a similar answer. Your answer would be the negative 1, the 1/2, multiplicity 2, the 1, the 2i, well, the 2i and the negative 2i. So be sure when you're answering complex questions, like let me restate that. Be sure when you're asked to solve or factor that you go all the way down to the complex. The only time I want you to ever stop before going to complex is when you are specifically asked to factor into irreducible factors. That irreducible phrase is telling you don't go all the way to complexes. Other than that, I want you to go all that way to the complex solutions. So, hopefully this was somewhat helpful. If you have questions on it, let me know. On the back of this, or the second page, should be a problem that you can try for yourself. Do that. Let me know how it goes. And if there's anything I can do to help, as always, let me know.